Hello everyone, we are Team Spike. My name is Hanbin. This is Shuheng and Jingxuan. Our project is Adaptive Network Filter. Nowadays, online shopping really play an important role in our daily lives. So what do people really care about? First of all, they care about whether the quality of the product is good or not. The second thing they really care about is whether the product can arrive as soon as possible. So fast delivery really play an important role in our daily lives. In the meantime, however, the terrorists may also use the fast delivery to deliver the bombs or the drugs, which may also endanger our daily lives. So in past, the fast delivery companies may use the workers and dogs to manually scan all the package and identify the dangerous package. However, what if the Black Friday comes? Then with such a large amount of package, how do they deal with it? Definitely the workers and the dogs cannot work. So they may use the machines, for example, like the X-ray machine to scan all the package to accelerate the process. Or even better, they may use combined with the computers to automatically scan the package. The same thing also happening in the internet. The hackers may also use the internet to hack into our daily lives. For example, they may hack into the hidden cameras, like the security cameras at our homes. They may also hack into the iCloud account to steal some kind of like the sensitive photos. They may also steal like hack into our pension money bank account, steal our pension money. Imagine that if the hackers steal your pension money, what will happen? So why is so hard to prevent this kind of the attack? First of all, let's look at some data. From 2000 to 2016, the internet users has increased by over 700%, which means that the network traffic has increased significantly. Over half billion of the personal information records has been stolen or lost in 2005, and among them, over 36% of the stolen information are medical information. We all know that the medical information are really sensitive and private. So imagine if this kind of information reached to the bad guys' hands, what will happen? So why is so hard to prevent these kind of things from happening? First of all, the internet traffic has increased significantly, which makes it so hard to monitor all the informations. The second reason is that it's really hard to implement the payload filtering with software because the delay of software is really large. So now let's let my teammate Shuheng to demonstrate the comparison between the software and hardware.
So why we use the hardware solution other than the existing software solution? First, let's have a look on the Intel solution. The Intel uses the hardware platform for the software nodes. They have the CPU of Intel Xeon E5, which is cost more than $1,800. They also have 32 gigabytes memory, which costs more than $300. With that powerful hardware platform, they can have a performance of over 535 megabits per second. However, with our hardware design, it is easier to get a performance of over 2000 megabits per second, and obviously we will have lower cost. The most up-to-date NetFPGA set is cost lower than $2,000 in all, and that is much cheaper than Intel's solution. And let's have a look at our system design. First, when we get a packet from the internet, we will send it into the IP filter first. Then we will get the header and the payload part from that packet. The packet itself will be sent to the packet filter, and the header sent to the blacklist and the payload for the bloom filter. The blacklist will check the IP address of that packet and to decide its results and send the result to the IP history part. The IP history part will get the confidence of that IP address, and then this confidence will be transferred to our pipeline part. At the same time, the bloom filter will scan the entire contents of that payload and get the results. The result will be sent to the pipeline. With that result of whether the packet content is good or bad, then the pipeline will calculate the new confidence for the IP history. The information inside the IP history will be updated, and IP history will share some IP information with the blacklist part. At the same time, the pipeline will also create the drop signal for the packet filter, and the packet filter will decide whether the good packet should be passed through the entire system and let it enter our local network, or the bad packet should be dropped. To look through our design, we have deep packet inspection technology to dig into the payload part. We do pattern matching to the content of that packet, and we use Bloom filter to help us finish the pattern matching part. This will give us some benefits in both speed and space. However, Bloom filter sometimes will have problems in false positive. For example, when we have a new packet of X, it will go through 3 different kinds of hash functions that will produce 3 different kinds of hash values. These 3 values will be considered as the index for location. Then we will check these locations inside a long bit vector, and the correspondent location will be set to 1. And when we have a new packet Y, it will be processed with the same hash functions and we get the locations. However, if the locations give us 1, 0, and 1, we are not sure that if that packet is inside our list, so we cannot very sure to say that this packet is good or bad. Under this circumstance, we may have the false positive. And when we get a clean packet Z, it will give us 3 clean 0 from that long bit vector, and we can say this packet is safe and we can let it into our local network. Then let my teammate Jingxuan to introduce the testing methodology of our system.
This slide will show the scenario how we are going to verify the function of our design. We are going to build a network with 6 nodes of different IP addresses. Each node can send data packets to the other nodes through a NetFPGA router. To illustrate how our adaptive network filter intercepts bad data packets and build IP address blacklist, let's take 3 nodes as example. IP address A could be a reliable and safe IP address, which always sends good data packets to the other nodes. In this case, it has quite high confidence value. Data packets from this IP address are always delivered to the destination. IP address B could be a benign one as well. It most often sends good data packets and extremely rare send few bad data packets. In this case, its confidence value will be affected a little bit, but still above the threshold value. If it sends good data packets later on, it will be no problem. However, IP address B could be a malignant IP address. By using IP spoofing, it sends lots of good data packets at the beginning to boost its confidence value. After that, it sends lots of bad data packets one after the other. However, according to our confidence calculation mechanism, its confidence value will drop below the threshold very quickly. If that happens, no other node can receive data packets from this IP address because it has been blacklisted. IP address C could be a bad IP address. It sends bad data packets from the beginning. As expected, its confidence value will be very low and be added to the blacklist shortly.
Here is our demo. First, let's download the bit file into our NetFPGA board. Then we can use RKD to send the routing table to the NetFPGA board. At present, we should be able to ping around. Now let's clear the screen for the next step. We will load the pattern into our Bloom filters memory. We choose the 16.5 as the first pattern. Here is the higher part of our pattern. And this is our lower 32-bit of our pattern. We choose 16.4 as our second pattern. Let's have a test on the node 1. First, we send a good packet to N2 without any pattern inside the content. The packet arrives in N2 and we receive the acknowledge from N2. Then we send a bad packet to N2. We choose the first pattern, 5. And you can see that the N2 will not receive the packet and it is blocked. For the convenience of test, we use the IP address of the receiver part to add into the blacklist so that we can test our nodes from one single node to the others. And we will not have to switch our node once it is blocked inside our blacklist. And now N1 is still able to ping around. However, as N2 is inside our blacklist, it will not be able to ping any other node. Let's test our second pattern with node 3 now. We directly send a bad packet to node 3. Use the second pattern, 4. And you can see that the pattern is blocked. As a result, N3 will also be blocked and added into the blacklist now. You can see that it is blocked from N0, and so will be for the other nodes. Thank you.